Hi everyone. In this video, we'll discuss dissolution method for capsules, gelatin issue and solutions. Capsule, especially gelatin capsules, behave very differently from tablets, and many dissolution failures actually come from the capsule cell, not the drug itself. Common issues include cell cross-linking, sticking to the vessel, floating, incomplete or delayed release. Because of these challenges, capsule dissolution methods are often more complex, and many QC labs struggle to get reproducible, regulatory acceptable results. That's why this topic is critical. Understanding capsule behavior helps you troubleshoot failures, design better methods, and avoid unnecessary OS results. Gelatin capsules are hydrophilic, meaning they readily absorb water. Because of this, their behavior can change with moisture exposure, aging, cross-linking, or even formulation leakage. All these factors affect how and when the capsule ruptures. Remember, in the capsule dissolution, the cell dissolves first, then drug is released. So, capsule performance depends not only on formulation inside but also on the integrity of the cell. Common problems include cross-linking, floating, sticking to the vessel, coning. Gelatin cells are also sensitive to media composition, temperature, degassing conditions. That's why capsule dissolution requires special attention and control. Gelatin behavior is highly sensitive to storage conditions. At low humidity, gelatin becomes brittle, and at high humidity, it becomes too soft and sticky. During dissolution, gelatin hydrates, swells, and rupture. The rupture time depends on several factors, that is cell thickness, plasticizer content, storage humidity, fill formulation, hydrophobic or hydrophilic. Another critical issue is chemical cross-linking. Aldehyde vapors from excipients, inks or packaging can react with gelatin and form cross-linking. This makes the cell harder to dissolve and delays rupture. Remember, gelatin is a protein, so it is sensitive to pH, aldehydes, and heat. That's why proper storage and formulation control are essential for reliable capsule dissolution. Let's understand the chemistry behind gelatin cross-linking. Aldehyde form covalent bonds between gelatin protein chains. This links the strand together and creates a tight network. As a result, the capsule cell turns into an insoluble rubbery film. This is a major cause of OS results, especially during stability studies with hygroscopic formulations or when exposed to reactive excipients. Common causes include aldehyde, heat, high humidity, peroxides. The impact: delayed rupture, incomplete dissolution, false failure of product performance. Regulatory solutions are: USP allows the use of enzymes, that is pepsin in acid stage, pancreatin in buffer stage. These enzymes digest the cross-linked gelatin, allowing true drug release. Assessment: always investigate cross-linking before blaming the formulation. Cross-linking often appears during accelerated stability studies, not always in fresh batches. So don't ignore it just because initial results look fine. Strong warning signs include slow or incomplete disintegration, visual gelatin flakes or bloom, capsule shape still visible in vessel, high failure rate at early time points, pellets or powder releasing very slowly. These are classic indicator of gelatin cross-linking. The biggest confirmation test: add enzyme to the medium. If dissolution improves after enzyme addition, then cross-linking not the formulation, is real problem. Always diagnose before changing the product. Here is the step-by-step approach to confirm gelatin cross-linking. First, test without enzyme. If the capsule fails dissolution, proceed to step 2. Repeat the test with enzyme. If it passes, this strongly confirms cross-linking. This proves the cell, not the formulation, is the root cause. USP Guidance 711. Use pepsin for acidic media, pH 1.2. Use pancreatin for media above pH 4.5. These enzymes digest the cross-linked gelatin proteins, allowing proper rupture and drug release. Important points. Enzyme use is required by USP when cross-linking is observed. Always verify enzymes do not interfere with your analytical method. Document everything for regulatory justification. Diagnose first, correct scientifically. Floating capsules are a common dissolution problem. This usually happens because of trapped air inside the capsule cell, which prevents proper wetting. The impact: delayed rupture, slow and inconsistent drug release, poor reproducibility. Practical solutions are: use sinkers, stainless steel, PTFE or USP compliant type, switch to basket apparatus if floating persists, degas the medium thoroughly to remove microbubbles. If needed, slightly increase RPM to improve batting. Remember, even smaller air bubbles can stick to the capsule surface and make it float. Good degassing reduces this problem significantly. Capsule sticking is another common issue in dissolution testing. As gelatin hydrates, it can become sticky, especially for hydrophobic fill formulations. This increases the chance of capsule adhering to the vessel bottom or wall. Why this matters? Sticking disturbs hydrodynamics, causes uneven exposure to media, leads to high variability and poor reproducibility. Contributing factors are vessel curvature, shaft or pedal misalignment, poor degassing, hydrophobic excipients. Practical solutions are: use basket apparatus to keep capsule suspended, slightly increase RPM to reduce settling, degas media properly to remove microbubbles, always check vessel and shaft alignment. Choosing the right apparatus is critical for capsule dissolution. USP apparatus burn. This eliminates floating completely, making it ideal for floating capsule, sticky cells, poorly wetting formulations. However, basket restricts movement, which can sometimes affect natural hydrodynamics. USP apparatus 2. This allows natural hydrodynamics and is preferred for when the capsule fully sinks, but you must control floating using sinkers, proper degassing, RPM optimization. Coning risk can be minimized by adjusting RPM, using proper vessel geometry, ensuring correct alignment. Medium selection is critical for capsules dissolution. Gelatin does not dissolve when above pH 8, so very alkaline media can delay cell rupture. Also, weakly basic drugs may interact with the cell and slow down swelling. That's why pH must be selected based on API solubility and absorption site. The medium must hydrate the gelatin effectively. Surfactants like SLS or twin can help by reducing surface tension, improve batting, prompting faster cell rupture. But remember, use surfactants only when justified. Avoid extreme pH conditions that reduce gelatin swelling, delay rupture, create non-physiological conditions. Right pH, proper wetting equal to reliable capsule dissolution method. Hydrodynamics play a major role in capsule dissolution. For most capsules, the typical RPM range is 50 to 75. What happens at different speeds? Too low RPM, slow batting, delayed cell rupture, poor reproducibility. Too high RPM, over aggressive mixing, risk of API leakage before full cell rupture can mask real formulation differences. That's why RPM must be optimized, not guessed. Best practice. Run trial experiment. Use both placebo capsule and API filled capsules. Observe rapture time, floating, sticking, and release pattern. On the basis of that, choose RPM. Filter winding studies are essential in capsule dissolution testing. Gelatin fragments can clog filters and interfere with sample clarity. That's why choosing the right filter type is critical. Best practices: use hydrophilic filters to reduce gelatin fouling. Typical pore size 0.45 micron. Pre-rinse filter when using surfactant containing media. Always check for analyte binding to the filter. Remember, a poor filter choice can cause false low results. Validate your filter, protect your data. To wrap up, always observe capsule behavior visually during method development. What you see in the vessel often explains what you measure in the data. Remember, gelatin cells add complexity to dissolution testing. Cross-linking requires enzyme-containing media. Floating and sticking can be solved using sinkers, basket, and proper de-icing, and you must optimize media composition, RPM, and filtration. Small visual cues like flakes, floating, or delayed rapture can prevent major OS investigation. Thank you for watching. If you found this explanation helpful, please like, share, and subscribe. And stay tuned because in this 62 video series, we will just deep dive through dissolution method development, validation, and many industry related examples. In the next video, we will discuss dissolution method development for multi-particulate system, pellets, beads, sprinkle capsules, and post your question in comment section. Thanks. See you in next video.